All right. Hello, everyone. I'm really happy to be here and speaking about this wonderful, weird experiment. We heard in the morning Ted talk about how quantum mechanics came about. And one of the things I would like to emphasize in this short talk is that quantum mechanics as a theory did not come about because some physicists felt they had to just dream up a new theory to explain, just to have a new theory. The theory came about because they were seeing things in nature that could not be explained with the previous theories, the classical physics that we had prior to quantum mechanics. So a lot of the advances in quantum mechanics came about because there were experimental results that were not making any sense with the old theories. And the double-slit experiment is one of such experiments where if you try to understand what is happening from the perspective of classical physics, it doesn't make sense. And because you want to explain what's happening, physicists come up with a theory, and in this case, quantum theory at least gives a mathematical way of understanding what is happening. It doesn't really explain what's happening from our classical point of view. So as we go through this experiment, it'll become clear what we're talking about. So the double-slit experiment is actually very simple and very easy to understand, which is why it is such an iconic experiment. It is an experiment that has had, well, it has a 200-year-old history. It was first done in the early 1800s by an English physicist called Thomas Young. And the reason he did this experiment was to try and understand the nature of light. And there had been a debate going on about the nature of light since the 1600s, primarily between Isaac Newton on one side, who was saying that light is made of particles. And by light, everything, like this light that is streaming down at us from the fluorescent lamps, Newton's idea was that this is made of individual particles. And there were other physicists who were arguing that no, light is wave-like in nature, just like sound waves or other kinds of waves. And for a good while, from the late 1600s to most of the 1700s, Newton's ideas were considered to be correct, that light is made of particles. And then Thomas Young decided to do this experiment, which then ended up showing that actually no, light behaves like a wave. And what is the experiment? The experiment is actually very, very simple. It is so simple that it will actually, when we are done going through it, it will make you cry because you cannot explain it. But it's extremely simple. And the idea is you take a source of light, you shine it at some opaque screen into which are cut two openings or two slits, right? So the light can go through one opening or the other opening. And then on the other side is a screen. And the question is, what do you expect to see on the other side, right? So now, at the time that this experiment was done in the early 1800s, like I said, Isaac Newton's ideas that light is made of particles was the most dominant view. So if light is made of particles, then individual particles are going through one opening or the other opening, and that leads you to expect something as to what might happen on the other side. And basically, our expectation is that on the other side, you should see the particles of light piling up behind one of or the other open slit, right? This is what you would expect. It's as if you're firing grains of sand through the two slits, and the grains of sand are piling up behind the two open slits. So if light is made of particles, this is sort of what you think you would expect. And what Thomas Young did and showed was this is not how light behaves. So light behaves like a wave. And when Young did this experiment, he saw these bands of light and dark appearing on the other side. Instead of two strips of light, he saw alternate bands of light and dark and light and dark, right? And this can only be explained if light is behaving like a wave. It hits the two slits, and then from each slit, new sets of waves start coming out, and then these two sets of waves expand and eventually interfere, and the interference creates this pattern of light and dark and light and dark. You can imagine this by thinking about a very, very still lake on which you drop two stones, right? At the point where you drop a stone, you'll get a wave coming out. And at a point where you drop the other stone, you get another set of waves coming out. These two waves will expand and eventually they'll interfere. And interference simply means that points where one wave is at the highest, and if it meets the other wave also at the same time where the second wave is at the highest, you will get a high level of water. And if one crest interferes with the trough of another wave, you'll get destructive interference and the water level will be lower. So Thomas Young was showing that light is possibly also behaving exactly like that, where it's wave-like in nature, and the two sets of waves that are coming out from the two slits are interfering and creating these bands of light and dark, right? So this was the early 1800s, and for most of the 1800s, this theory held sway. Basically, Maxwell came along with his theory of electromagnetic theory, and indeed showed mathematically why we should treat light like a wave. So everyone kind of accepted that, okay, light is wave-like in nature. But then 1900s, early 1900s, things started changing with the birth of quantum mechanics. And we've already mentioned by now that when quantum mechanics came about, it became very clear that energy comes in individual quanta. So if you take energy of any frequency, that energy cannot be subdivided any further than the smallest unit of energy. This smallest unit of energy is called a quantum of energy. Light is also a form of energy, which means that light also comes in quanta. That every frequency of light, so for instance, so this is a green laser light. That's not really a photon, but this green laser light is made up of it's light of a given frequency, which means that this light, if you had to divide it into smaller and smaller units of energy, finally you will hit a bottom and you can't divide that any further, right? So 1905 was when Albert Einstein made an argument that light should also come in quanta. Light is made of particles, right? And these quanta are particles. Now, when you try and do the double slit experiment, it becomes really strange, right? So if you go back to this figure. Now we take the laser pointer, this laser pointer, right? Imagine that this is a laser pointer shooting laser light at the two slits, and if you had a lot of light, you would get that wave pattern on the other side. Now imagine you are able to turn down the laser light to the point where individual photons are coming out through the laser device. So one photon at a time is going through the two slits. I just remember we were supposed to do an experiment. Should we do that before I continue? Yeah? All right. Sorry, we actually had a demonstration with the laser light that I completely forgot about. Let's switch off the lights and we'll show you how the classical version of this looks. Because we can't do a quantum experiment here, but we can show you a... So let's do one without the wire. So this is just a laser beam, right? Now, what Nima is going to do is he's going to put a wire across the laser source. So what that's doing is it's creating two paths for the light to take. On one side of the wire and from the other side of the wire, and those two paths are now interfering. If light was made of particles, you would see a sharp shadow of the wire. But because light is made of waves, the laser light is going on both sides of the wire and interfering, and you're sort of able to see at the very center is the brightest constructive interference, but you can see little, it's not terribly clear, but you can see little fringes, light and dark that go off to the edges. So those are clear signs that light is behaving like a wave and interfering with itself. So can you see? That's beautiful. Yeah. So this was an experiment done with almost like what Thomas Young would have done with a classical source of light, like lots of light. You're not dealing with individual particles of light, but a lot of light. So in this case you can treat it as a wave, and you can see the interference pattern. But now, when quantum mechanics came about, it became very clear that light actually is made of individual quanta. And now if you have a source of light that is sending out one quanta at a time, what would you expect with the same experiment, right? What is it expect? It's as if you have a gun that is shooting out little particles of sand, and the particles of sand have to go through the slits, and you're expecting to see some pattern on the other side, but you're sending now one at a time, not a lot, just one at a time. What does your intuition say should happen on the other side? Anyone? I think we sort of expect this now, right? We think that we are sending individual particles. The particles have to go through the left slit or the right slit, and on the other side they should pile up behind the two slits. This is what should happen. At least that's our classical intuition. And it turns out that's not what happens. This is the pattern that you get, right? Even if you're sending individual photons one at a time through the double slit, on the other side, over time, this pattern builds up. So imagine on the other side it's a photographic plate which is recording the arrival of the photons, a photon being the name for one quantum of light. So on the other side, the photons are hitting the photographic plate, the plate is registering where the photon hit, and over time you will see that the pattern builds up. So as you're sending individual photons one by one, you can see that at a certain, let's say after 10 seconds you see the first pattern, this one, after 20 seconds you see that, after 30 seconds that, after 40 seconds that. Basically, you're seeing an interference pattern. But here's the really puzzling thing. What is interfering with what? Because you generated a single particle, right, from your source, from your laser source, or whatever source you had, you generated one particle, you sent it through the double slit. On the other side, you detected one particle. In order for something to interfere, or in order for there to be an interference pattern, something has to go through both slits at once. So what is going through both slits at once, right? So these are the questions that now you can start asking just based on this one simple experiment. We have created a single particle, we have detected a single particle, and yet we are seeing an interference pattern. The photons are only going to certain regions on the photographic plate on the other side. They're not going to, like here, the photons only go to the regions where eventually you end up with a lot of light. They don't go to regions where eventually you'll see darkness, right? But every single photon is doing something weird. Every single photon is behaving as if it's a wave. It's only going to certain regions which represent constructive interference, and it's not going to regions that represent destructive interference. But it's a single photon. How can we say that a single photon goes through both slits at once, right? So that kind of conceptual question comes up when you try to understand what is happening with this experiment. You also cannot, there's something else that is happening here that is really weird. You saw that there are a lot of dots that are made by individual photons as they go. You cannot predict with certainty what any given photon will do. You can only talk in terms of the probability that a photon will go to one of the regions that will eventually make up the bright strip of light. Right? So for any given photon, you can only say, oh, there is a 50% chance that it will go to the center, 20% chance that it will go to the side this way, 20% chance that it will go to the side on the other side, right? So you can only talk in terms of probabilities. And if you just take a single photon, there is no way to deterministically tell where it's going to go, right? So when the detection eventually happens, the photon will appear in one of those places where there was a non-zero probability of the photon being found, but exactly where it will end up, you cannot say before you actually look for it. And so you can also ask this question, does the photon have a trajectory, right? Now if I have a cricket ball in my hand and I throw the cricket ball into the audience, and I know exactly all the forces that are acting on the ball, including the force of gravity, etc., I can predict exactly where exactly the path that the cricket ball will take from my hand to somebody's head out there, right? Exactly. If I'm a good, careful thrower, I can aim and predict the trajectory. It turns out that you can know everything, seemingly everything about the photon, and you still cannot predict where it will go, which sort of means that you cannot talk of the photon as having a trajectory. Because you can't tell exactly where it will end up, you cannot then say that it had any kind of trajectory. And the other curious thing about this experiment is your classical intuition, your knowledge of how the world works in everyday life is telling you that no, this is a single particle. It has to go through one slit or the other. How can it go through both? Let me just put a detector to see which path it's taking. Is it going through the left slit or is it going through the right slit? If you could come up with a way in which you can detect which path the photon is taking, either the right or the left slit, without destroying the photon, and there are ways in which you can do that now, it turns out that the interference pattern disappears, right? So if you try to see which path the photon is taking, then it will behave like a particle. You will see this pattern. If you try to see which path the photon is taking, it will act like a particle. It will either go through the left slit or the right slit. But if you try not to see what the photon is doing until you do the detection on the photographic plate, then it seems to behave like a wave as if it's going through both slits at the same time, and you get this interference pattern, right? So this simple experiment, this is something that can be done in any physics lab. You can start asking you can start asking questions about some really fundamental aspects of the nature of reality. So in order to explain what's happening here, quantum physicists had to come up with the mathematics to explain. And one of the fundamental things about quantum mechanics is that any quantum system, in this case a particle of light, which is a quantum particle, is represented by something called a wave function. It is just a way of representing or modeling the state of the particle of light. So in this case, let's say that the wave function is modeling the position of the photon. So when you create the photon, the wave function has a very definite value at the point where the particle is created, and it's nearly zero everywhere else. It's basically telling you that the particle is there where it was created. Now the particle starts moving towards the double slit. Mathematically, what happens is that the wave function, which Ted had mentioned in his talk about Schrodinger's equation, you can calculate how the wave function changes using this equation called the Schrodinger equation, and the wave function starts spreading. So now remember, we're not talking of the exact position of the photon. We're just talking of the mathematical object that represents the state of the photon. That mathematical object starts spreading like a wave. It hits the two slits. It behaves exactly like any wave would. When it hits the two slits, you start getting two sets of waves coming out from the other side. But these are not waves of something real. These are waves of this mathematical abstraction called a wave function, right? Which is representing the state of where the photon might be. And that wave function spreads, interferes, and finally, when you look at the state of the wave function just before it encounters the photographic plate, it can tell you the probability of finding the photon if you were to look for it. So the photographic plate, which is a detector, is an act of looking, right? So the photographic plate is trying to detect where the photon is, and the wave function will tell you that, oh, the photon might be found with a very high probability here, with very low probability here, with high probability here, and so on. And that's what happens. As soon as the wave function mathematically meets the detector, it suddenly collapses from being spread out to being in one location. But exactly where that location will be is not determinate. It is indeterminate. It will happen randomly based on the probabilities, right? So this is a very essential concept in quantum mechanics, the concept of a wave function. So every quantum system is represented by its wave function. It's the wave function that evolves using quantum mechanics, using the Schrodinger equation. And the question is, what is this wave function? Is this wave function real? Or is it just a representation of our knowledge about reality? These answers are not yet known. And the double slit at least allows you to understand what these questions are. The other thing that the double slit allows you to understand is this idea of quantum superposition. You would have all heard of this idea in quantum mechanics that something can exist in two places at once. Well, actually, that's really not entirely accurate. What quantum mechanics is saying is that the wave function is going through both slits in this case, and there are two new wave functions that are coming out from the other side, and that they are interfering. And so the entire quantum system is in a superposition of these two states. That does not mean that the photon actually went through both slits or the photon is in multiple places at once. It's just a way in which we talk about what the mathematics might be saying. The mathematics is just an abstraction, and eventually it allows you to calculate the probability of finding the photon at some place, right? So quantum superposition is really a statement about what the mathematics is telling us is happening in terms of the wave function. It really doesn't, it's not really a statement that accurately means that the photon is actually in two places at once. We don't actually know, at least from the mathematics, we don't really know where the photon is until you do a detection. The other thing that is highlighted by this experiment is this idea of wave-particle duality. This is very clear. If you don't try to see which path the photon is taking, it seems to take both paths at once, interferes with itself, and it behaves like a wave. If you try to see which path it takes, it behaves like a particle, right? So your choice of the experimental apparatus, if you have an apparatus that is trying to see which path the photon or any particle is taking, then it behaves like a particle. But if you say, I'm not going to look at the particle, what happened here? But if you have the experiment set up so that you're not worried about the particle nature, then it will behave like a wave. And the words are deliberately being used here, like a wave or as if it's acting like a particle. We really don't know if that's what's happening. We're just interpreting the mathematics to say that's how we're thinking about what might be happening. There's also this idea of realism versus non-realism that you can, oh, hang on. No, determinism versus non. So this we just talked about a little earlier. In this particular case, if it was a classical system, if you knew everything there was to know about the system, all the forces acting on it, you can deterministically predict what will happen to the system in a time in the future, right? When I throw the cricket ball, I can tell you exactly what will happen to it. But with a quantum system, you can only talk in terms of probabilities. So nature seems to be indeterminate at the quantum level, right? And there are other fundamental questions that can be understood, if not answered, by thinking about the double slit. One is the collapse of the wave function. Remember I said that the wave function goes through both slits, expands, interferes, and then at the moment when the photographic plate detects the photon, the wave function collapses from being this spread out thing. When it's spread out, it means that the photon has a probability of being found in a lot of different places if you choose to look for it. But the moment the detection happens, then the photon will appear in one of the places where there was a non-zero probability of it existing where you to look for it. So this process where the probability goes from being spread out all over the place to actual localization of the photon is called the collapse of the wave function. There's also conceptual issues like realism versus non-realism. Now, realism is the idea that things out there exist independent of observers, that if I throw the cricket ball, nobody is going to argue that the cricket ball doesn't exist if I don't look at it, right? But in the case of a photon, it turns out that, at least in the way the mathematics of quantum mechanics is at the present time, one seems to be led to think about the fact that the photon actually does not exist in any real sense until there is an observation, because you cannot talk about its trajectory from the source to the detector in any deterministic way. Because there is no deterministic trajectory, you cannot talk of the photon as being real until there's a measurement, until there's an observation. So, and theories which kind of deny reality are called non-realistic theories, or theories that deny reality until there's an observation can be thought of as non-realistic theories. And these are the kind of arguments that come about when you start thinking about quantum mechanics. Wave function, questions about the wave function, is it real? Or is it just a representation of what's happening? If it is not real, then what is going through both slits? Because something is definitely going through both slits. It's not the individual photon, because if you put a detector to see which side the photon takes, it's either left or right. It never goes through both simultaneously. So if the wave function is not real, then what goes through both slits? But if you say the wave function is real, then that opens up a lot of other conceptual questions. So this experiment, I just wanted to show you that just by using this simple experiment, you can start understanding the very, very difficult conceptual questions that quantum mechanics throws up. It's not as if there are answers yet, but the conceptual difficulties at least can be understood. Right. So, thanks.
Let's open up for some questions from the monks on my left here.
So my question is that when you did the experiment with this green laser, without that wire in front of it, there's only one spot. But when you put that wire in front of it, there are many spots on the screen. So is it the wire that is creating these spots, or there could be other reasons why we can see this kind of spots, multiple spots?
So what the wire is doing, it's basically creating two paths for the light to take, on the left side of the wire and the right side of the wire. And it's similar to what the double slit experiment does. It gives the light two paths to take, right? So in the case of a wave, if you think of a wave of water that encounters a rock, the water then goes on both sides, and then it keeps going on both sides until eventually it meets. And so there are two waves that go on both sides of the rock, either side of the rock, and then eventually they meet and interfere. That's something similar is happening with light. And you're treating not individual particles of light, but a lot of light. It acts like a wave. It goes around the wire and then eventually meets and creates, and the spots that you see is the interference pattern of the two waves meeting.
Chizan dires tanda nganzo ki zinra khnang lo takji che di khada ucha di yores lavim bena tanda del ane shurga ni den ki takji che tön suas chiza din nang sing chagi yores shurga ni den ki takji khnang lo la shurga ni se kapsla dine kirang ka pha tang wi ki wudu di ane dosa ki lamga ni su yores ane dosa ki lamga ni su che ane gabla tu yung du sambala konzo ki lap thapa se tanda interference lo lam thapa se konzo lamga ni ne lebe ki lap dun so ane thap che thama di ki gablo ki thayu ki tingla ane tanda lam thap ki remote di thuyung yorwas cheza da tanda dakji dik nanglo la kirang ki tanda ane we jangku dik dun de la lo ku chi sha yung du sambala lo ku dik yen yu ni ne we jangku dun su dosa ki lamga ni su wares ni su che ane gabla tu yung du di pe khado yoris la min bena nang gyu changbu ki chu ki mal do chu min bena ane do de tu yung du sambala changbu de chega chi ji du su ruwas ina ane do de ge cha we jela chu dun su che li res din nang shin ane tanda ane we jangku dun su du su le yung du sambala lo ku dik tu yung du sambala dik yen yu ni ne chin che lamga ni cha gabla su tu yung du sambala tal ding la lamga ni chimbe gu gemsen te ne ane su yung ni ke we dun su chik gang dong du yores tab du yores tab yung du sambala ane lab ki ane nam gyu tön che ane ngang su jab ke thayu ke ting la ane we yosa mesa la chi rimu chi tung do ondela ane lam tab ki number se ondela yores.
My question is, what does the new double slit experiment actually show?
So if you're doing the double slit experiment with individual particles, so that there is only one particle going through the double slit at any one time, you still see an interference pattern. And so it really raises questions about what is interfering with what. It's as if each particle is interfering with itself, right? It's as if each particle is going through both slits at once. And so, of course, that is not what's happening. We don't know exactly what's happening. The mathematics is used to explain the results, and the mathematics is then interpreted in various different ways to understand what might be happening in reality, right? But what the new double slit experiment done with individual particles really shows that the quantum world does not make sense if we just use our classical intuitions to understand, because our classical intuition is saying that the particle cannot go through both slits at once. But here something is going through both slits at once. If it's not an individual particle, then what is it that's going through both slits at once?
tanda shurga nyinde ki takche shto tanda remotion sa digang tyung du zambala tene pha droya ke we di module si do dun tamu we ke ane nebo chungshu tamu re tu du yores tu jigla re chimbi imbina ya ane tandung khartung yores la bimbena la bangbo do nangshin ki lamtab ki remus ya di jab ki thayu ki tinglan thong yung yores cheza ta dila du zambala ngazu thiwang gong yokbo du li yores ane we du chik mishi chime we imbena ane ko 태도 진이 디 가르님도 동구여레스 고랑고랑 그 동구여레스 순님도 태도 지기여레스 대가나신 동이 찍미시 매빈베나 도살람가 니 도스 니네 아니 고랑 두직라 도살람가 니니 침버레스 야메나 안 컨데스 차오레스야 디 응주 하구요 마레스 임베나야 탄다 아니 랍게 첼레스기 탄다 지긴 도단시도 지기 코르탄 디기 토네 아니 키랑 베두 레레 아니 퇴주 케직 레레 땅빈비나 아니 갑로로 포비 kapsula lamtab ki remote dendeji yongsigre posa dendeji posigre samya ki seya ki ani nezu deshe turma do uyo nezu lamgal kharchin yore shurga ninga ni chin yore we chin yo marwe sunyam do dung yor se denzu tanda sing yo mares di shemba ha ko kapsula ani gablo ki remote shik du yores me ocha du yores.
Since we all are well aware that everything that we see by our eyes are made of particles, and since we are talking about light, as you have mentioned that light also travels in a wave. So here the question is this, that does the particle behave as a wave? If yes, then is it measurable or not?
Yeah, and in fact, that is one of the key conceptual ideas behind quantum mechanics, that everything can be thought of as having either wave nature or particle nature, right? So down from a single particle upwards, even you and I, according to quantum mechanics, have wave nature and particle nature, but because of our size, we don't see our wave nature. We act like particles, like we're in one place. Yeah, so if you're talking of a single particle, it is displaying its wave nature. Even though we're talking of a single particle, in the double slit experiment, it is displaying its wave nature if you choose to look at its wave nature, but it will display its particle nature if you choose to look at its particle nature.
Tang nganzu sangma ane dundeng kutumbar was. Jaza kirang ke wedu pe la shane ane dudun zo lab ke ane rangshin yore sig was. Jaza ta nganzu ane lab ke du kutumbar che dil lab ke rangshin tuya yo bi mena lab ke rangshin tuya bad senje tuya yor wesne tiwadi. Ta gelang korang ke lende on de res. Sedu ngam rigbe ke namsha shil shav imbe na ane jigden nang yobe ke ngobu dunzo chechung sangma la ane lab da du ke ane namgur ninga tuya tuya ke niba yores. Jaza ane 이나야 간조다 오보 락바 된조 아니 가르차루 요레스 라빈베나 남기 랍기 남바디 조 명문바 차루 요레스 류기 남바디 아니 슈크체르 차체 아니 간조 디 오보 타문능시 아니 메와 차도야다 하모야 되는 요말 고생해바디 차루 요레스 다 이나야 아니 류 된조 레캬랑 땡도 잠바 랍기 남규르 응야게 딱지 지ing도 잠발라 랍기 남규르 응용 요레스 류기 남규르 응야게 딱지 지ing도 잠발라 류기 남규르 땡 요레스 dila du zambala mo bo denzo la labdu ninge ke ane rangshi ane sungdei badi ane tentu yores yigi yores.
Let's hear from Tupten La, and then maybe a question from the audience.
Thanks Anil for your explanation, and what my question will be is that does the interference pattern in the double slit experiment demonstrate the physical reality of superposition, wave particle duality, or both?
So the double slit experiment is demonstrating the reality of something called quantum superposition. What that means in real physical terms, we don't quite understand. The mathematics says that things, in this case, you can represent, the photon using its wave function. The wave function ends up going through both slits, and we use that mathematical abstraction to say that the photon is in a superposition of going through both slits at once, right? That's just a term to say that that's what the math is telling us, but it does not mean that the photon is actually going through both slits at once. It does not mean it's going to one or the other. I mean, we really don't know. So it's just a way of stating that the quantum system can exist in multiple states at once, at least in the mathematical sense. In terms of physical reality, it's really unclear what's happening.
Gila korang ki tiwa di tanda shurga nyindeng ke takje di kis ane tsedu ke ane nekapsula tanda nganzo music siya jorwa tanda superposition siya dida ane sungdeng ki rangshi siya di nying kangrung tungu yorwe nyinga tungu yorwe siya di tiwa dire dwa chiza shurga nyindeng ke takje di ke ane labdu sungdeng ki rangshi yinba di tungu yorwa tanji siya tsawa che ta music siya shita nul chik tingla tsawa siya di khar tsawa siya yorwe siya du zambala ane lab ki kecha yinba da nganzo dila lab chik siya chiza di khar siya yorwe lab yinba na cheju nyi ane tujigla ane jik gangla jik domba nangshi yowa yoy meki ane dinek keja kuyores ta tanda dinepa dronyin ki wudu di ane shurka nyi yoybe nanglo ne shurka nyingala ane tunyam dendrowa yorwes yamena ane labda duki ane chechu di ane tuzu jigla ane tunyamba dinde yungu yorwe siya dik keja res cheza ta di ngozu nganzu dokship cheya yomare la saswas ina ta zig tohne tanda labki chile siya dik tohne ane ko yungu yowa deshi jagdan jik nye dik yores.
Maybe a quick question from someone in the audience? Anybody? Yes, please.
Sir, as you said that through that double slit, Young's double slit, light scatters while we pass through it. So instead of that slit, if we would have holes in that, so through holes, is it possible that the light scatters or it remains the same? Because most of the time when we pass light through a hole, I think in the second screen as well, we see the spot only. We don't see light scattering.
So it really depends on the color of the light. For instance, if you're just So the frequency of light that you're using and the size of the hole, it depends on if the hole is too big, you will just see a spot on the other side. But if the hole is small enough, then you will get, the light will spread out from the other side. In a way, it's called a diffraction pattern. If you have 2 holes instead of 2 slits, and if the holes are spaced, in the right distance apart, and if they're the same size, I mean, if they're of the appropriate size, you will get an interference pattern on the other side. But it won't be long strips. It'll be, my suspicion is it'll be dots. Right. The basic idea is any aperture through which the light goes, depending on the size of the hole and the frequency of the light, there is a relationship. And if the dimensions are correct, you will get diffraction on the other side, interference. Right. That's.
그래서 길랑코나 디오디 단당한조 쇼르가니데 시주 잠발라 아니 지가 데네 카디 아니 링부시마 니 수기도 왔어서 카 링부니 마소 체체 아니 고고 춘준이 스웨빈베나 아니 갑로라 로드 웨드 도두 잠발라 람탑 기르모드 통게 레베스 라소 지자다 코랑기 세야치 빈베나디 통그레스 임베나 야 통알라 카르구레스 라빈베나 파 드링기 카디 아니 춘준 구레스 춘준 여와디 가주스 구레스 가주스 춘준 고레스 야디 데네 파 드링기 웨디 킹안소 프리퀀시라는 되주시로 되주기 아니 체발라 아니 라리 요레스 단 되주 체벌 치라바 찍라 램베키 아니 딘데 이공 춘준이 스웨비베나 갑라 리무근 도단디 sob다디 로가 밥게 레마도 아니 단다 람탑기 리무디 밥게 요와디 아니 녜버레스